of Physics, I would like to start the program. So, before going to start the session, I would just request Professor J.K. Pandey sir to say a few words.
Yes, sir. Thank you, Dr. Niyogi. Good morning, everyone. And I would try to say a few words only. But first of all, I am really happy, honored to formally welcome Professor Chandrasekhar. Grateful for his time on behalf of all my students who were consistently asking about this program. And this is Saturday. It's a kind of zero class day, but still they are joining us, and they'll keep joining, I think, in between. So thank you, Professor Chandrasekhar, for your time. And the topic which we have selected today, one of the rare combination where students can get benefit by knowing the basics, as well as people who are working in in this area as a researcher, they will understand the challenges of this purely kind of basic thing that is being studied since so many years. And I should say quantum mechanics is something that people might not have given the name quantum, but they were aware of this thing. So it's a great initiative by HOD, by Professor Tamal Mukherjee, Professor Niyogi, and whole team. And I wish you all the best. And please allow students to ask questions. So you may write or inform in advance that whatever they want to know, they are welcome to write in the chat box even during the presentation. So then we will take each question one by one. So from my side, I think let's start. Everyone was waiting. I'm sorry for 1 or 2 minute delay. Please, over to you, Dr. Niyogi.
Okay, thank you, sir. Thank you for your nice word. So it is really a good opportunity for us faculty members and also the students to have such a nice presentation. I hope that in the 1.5 hours, it will be a very great hours for all of us. And without delay, I would like to request now Professor Mukherjee, Tamal Kumar Mukherjee, to introduce our speaker. Okay, so now Tamal sir, please.
Yeah. So before we start, we would like to say a few words about the sad news or the sad things that happened yesterday. So we are very sad that Professor T. Padmanabhan, who is commonly known to us as Paddy, left us, and we want to express our deepest condolence to his family and friends, and would like to pray that his soul rest in peace. But the best way to express our gratitude and our respect to him is to continue doing physics, what we are doing. So that is what we are going to do today. As there is a common saying that the show must go on. So with this, we all pray for his soul to rest in peace. So now let us come back to our program. So we are very fortunate to have Dr. Chandrasekhar with us. So he's one of the leading scientists working in the area of quantum information and quantum computations. So Dr. Chandrasekhar completed his PhD from National College, Bangalore in India. Then he moved to University of Oxford on Rhodes Scholarship. So at Oxford, he worked on experimental Bose-Einstein condensation for slightly over 2 years in ultra-cold quantum matter group under Professor C.J. Foote. So while at Oxford, his interest towards theoretical aspect of quantum information theory and quantum computing grew, and that led to him to move on to Waterloo, Canada, in the Institute of Quantum Computing and Perimeter Institute of Theoretical Physics. So in Waterloo, he worked under the guidelines of Professor R. Raffiami. Maybe I'm pronouncing it wrong, but Anyway, I mean, he completed his PhD in the year of 2009. He also worked in University College Cork, Okinawa Institute of Science and Technology in Japan. So then he returned to India and got Ramanujan Fellowship. In India, he first joined Indian Institute of Sciences, ISC at Bangalore as adjunct faculty, and subsequently he became a faculty member at the Institute of Mathematical Sciences, Chennai. So among the various awards and fellowship he received, the few I would like to mention, for example, Rhodes Scholarship, Mike and Ofehit Lazaritz Fellowship, and Ramanujan Fellowship. So he basically, his broad area of interest is basically quantum information and quantum computations. So since all of us are looking forward to what he has in store for us, so let us please welcome Dr. Chandrasekhar again, and over to you, sir. Please.
Thank you very much, Dr. Tamal, and I also thank all the organizers, the Dean, HOD of the university, and in students. It's a great pleasure to talk to students. When they are in large numbers, it's always a pleasure for us. Unfortunately, I can't see you in person and then interact, but still, as Dr. Tamal mentioned, the show must go on. Whether it's pandemic or whatever it is, we have to keep doing our sciences the best. So I've tried to, the title itself says, Quantum Realm, a great way for frontier technology. So we are at the edge, or we are in the edge of evolving or moving forward of advanced technology, which are based on quantum mechanical principle. Quantum physics is not new. It's already been a decade. And we all have got introduced to it in our schools, probably like later part of our schools. There is something called as quantum photoelectric effect, and whole of physics, or the nature can be described to the best using quantum mechanics. So it's not new. It has been there for 100 years. For the last 20 years, we have learned to handle atoms. We have learned to handle photons and try to have some good control over them, so that we can make use of it, of that to technology. So today I will try to give you a mix of everything. For example, I think it was Dean was mentioning that there are a lot of elementary part, probably, so to give you some idea of what I call as a phenomenon of quantum sciences or quantum physics, and what we see as a resource in that for technology, so that you will get a bigger picture, even if you have a very basic idea, or probably you are in a very jovial mode of not looking into details. I will try to give you a basic foundations of quantum physics and its phenomena in first few slides, and then go to the need of evolving into quantum technology. Okay. So let's see. Okay. So what is quantum? So this is something which we all have studied. I know it might be a bit introductory for professors, but for students, it's a good review. Planck's quantum theory of radiation and photoelectric effect and Bohr's hypothesis of electrons going around in an atom. And if we consider an atom, we have nucleus and we have electrons which goes around. It does not collapse into a nucleus, neither it bounces out of an atom. So it remains stable. So to understand how atoms are stable, how electrons move around, people had to develop hypothesis, or try to understand or come up with a theory to fit into what we observe in nature. And photoelectric effect is one of the famous contribution from Einstein, for which he also got Nobel Prize, which explained about how you have a photon which enters. I think there is a scheme here. Okay, so you have light from nature, or from some source. It can be a sun. It enters into a material. Electrons are kicked out, and it comes out. So there is some minimum energy of light required for electrons to get kicked. It's not like a continuous form. So there is some quanta. It comes in packets, and this is something with an hypothesis actually, which Einstein proposed, and later on it was verified experimentally. So it gave a birth. Now all these three concrete conceptual ideas and hypotheses gave birth to quantum theory. So after that, people started developing and building upon the whole structure into that. So I don't know, with last 30, 40 years, many things happened from 19 to 1940, Schrödinger's wave equation representation and understanding nucleus also, not just atom as a whole, what is happening inside nucleus, all of those things. I'll just quickly jump to something which we all know in various aspects, interference. So this is not new for us, okay? So waves interfere, water interferes. If you just go sit on the bank of on any water body, we see some interference effect coming in. Sound waves interfere. So interference is not a new pattern. This was known from classical theory, right? So it's a simple experiment. Probably most of you would have done in your laboratory, undergraduate laboratory, or you would have read of all these things. I can take a slit, a two-slit frame, like this, and then I can have a light source. When this light source hits a slit, the light which is entering gets blocked, and only a small fraction of them go. When they come out, it comes as two sources of light from these 2 points. When these two sources come out, then again they start interfering, and then we end up having an interference pattern if we record it on a screen. So this says, in general, light is wave, right? So it means if I'm sending a light and splitting into 2 parts as 2 independent sources, then they let them interfere, I end up getting interference pattern. And there is something which we all have studied in optics, and Young's double slit experiment shows what is the interference and how the phase. So these details are there, you don't have to worry about them, but we see a pattern like this, interference pattern. So this is first part. So how ideas evolved, just to see that. And next, the same thing, if you are doing with a stream of light, for example, I block just one path and then just send a light. It's again a light. Then I would see intensity of wave passing only through one slit, and there is no any interference coming in, and it will be of particle nature. It means that you don't have anything, it comes out. Now the moment I open 2, so it means that if I'm seeing light as a wave, I end up getting interference pattern. But now I reduce the intensities of it and try to send them as particles, so that you are just trying to bump. It can be light or it can be electron, and we would end up seeing again interference pattern like this, but not like a wave if it comes out. So this kind of says there is some wave behavior even in particle nature. So these are all a thought experiment, but I will come to quantum mechanical aspects of it. Right? When you have even particle, it is seen more like a wave when both the slits are open. Only when one slit are open, we would end up seeing like a particle. Okay? Now, this completely defines the way wave-particle duality is understood. And this is one of the most fundamental aspects which is currently exploited for quantum technologies. Okay, so which is very important. It looks very simple. It looks very something which you all have studied. People know it from like last 80, 90 years, but we have learned to control them and see them clearly. So what does this say? Now I can take a weak source of light. It means that because we know. Einstein had said about photoelectric effect, many experiments had verified that photon comes as a packet. Now, if I'm sending photons, then I should, in principle, just get these things, because these are like particles. If particles are hitting the screen, I should only get these 2 patterns coming out of these 2 slits. But in reality, we only see them as waves. There will be some interference effect. Now, how did people understand this? So this experiment says that this is somebody who is watching at it. If I'm keeping track of a particle which is coming, this particle comes out from a source, photon comes out from a source, it enters the first slit and it falls in the screen. So if I'm keeping track, dice are open here. If I'm observing which path the particle is going, then I would end up having a particle nature. If I'm not observing, if I'm just closing eyes, then there is an interference effect. Of course, when I say closing eyes, I'm being a bit more dramatic here. But when we say if you are not keeping track of it, which means that if you are not making measurements on a photon, if you are not following it completely, then we are seeing a wave nature, which again, you can connect it to something which we know about uncertainty principle. In simple, we say, momentum and position of a particle cannot be measured, because any particle, when we are looking at a microscopic scale, they have a wave nature. It means that you can't fix its position But if I'm trying to fix its position, it means that I'm forcing it to be observed there. But if I'm just leaving it, there is some internal energy in them which keep them oscillatory, which means that the position is not fixed to one point, it is around that point. That small wavy vibrational behavior of those particles gives them wave nature in it. So it means that if I'm not observing, then the particle which comes here will take possibility of splits into both the path. Splits in the sense, actually it splits. I'll give another example to look at. Splits in the sense it will have a wave nature when it's entering these two slits and ends up being interference. Of course, when people do experiments of that to that precision, the slit should be very close. There should be two slits, but they should be very close so that it actually takes two paths simultaneously. So these experiments have been done in only like last 30-40 years. Before that, theoretically, the ideas were built and they said if these experiments are done, this is what we will observe. So here there are statements which I probably would have read by now. So I just try to read it to give you an idea. Knowing which path or slit the photon travels through is a form of measurement. When I said we are observing, then it's, if you are measuring, we are only studying its particle behavior. If I'm keeping track of all the path it is taking. If I'm not measuring, then we have a wave nature. So it is in our hand to extract the wave and particle nature together. This is the first step where when I said, see, there are advantages of wave nature, there are advantages of particle nature. If something comes as this is a quantum system or a photon or an atom, which has both wave and particle nature, and I can decide to extract the wave nature of it or a particle nature of it, or both of them together, then it means that there is some advantage which I'm getting out of this. So currently we are in a position to extract both wave and particle behavior of such small atoms or photons or electron spins or whatever, the quantum mechanical systems, means small microscopical systems. And so I have an ability, or we have engineered to an extent, so we can extract both of these features simultaneously. That's the first thing which comes handy to us. Okay, so this is just which path it takes. We will never be able to look at it. Interference, at the moment I'm keeping track of which path it is going, the interference phase. Now, that is first thing we have to remember, that there is both wave and particle nature, and measurement collapses the wave behavior in it. If I'm not measuring, then I have a wave behavior in it. It's all only things we have to remember. Now we'll go to another simple experiment. Okay. This says we need to establish that there is actually a photon which would behave a particle way, and then it actually goes. When I said here two slit, I'm saying that a photon which enters here, if I'm not observing, it actually goes to both paths. But then these are all strong statements. Right? How can one photon, can you split photon would be a question. Because we may not answer that right now. But how will it go in two? So if it's wave, then is it something breaks and then recombines? So these puzzles exist. So to understand that, we can take this another simple experiment, beam splitter, standard, undergraduate laboratory stuff, where it says if I'm sending a light and I have a beam splitter, it splits into two paths. If I'm sending a light of some large intensity, it's easy to see that two intensities will come at these 2 points. But if I'm sending a single photon, what happens? Okay, so to understand this, there is a simple experiment which people do, and been there in many undergraduate labs also. Probably in India we don't have a entangled photon source. I will not say much about that. I will introduce them later on, but let me say here, there are ways where I can simultaneously prepare and send two photons. Okay, so I can say that probably I have some technique I will manufacture, or I will generate two photons simultaneously coming out from some system. I will send one photon to a detector D0 here. Okay, another photon I'm going to send to another path to a beam splitter, which means in beam splitter it has to split and go to D1 and D2. Okay, there is no measurement here. We can actually map this to a two-slit experiment. Okay, so we just see this image and then you connect it to two-slit experiment also. It can be like a photon enters and this is like a two-slit, which means this is one path and this is another path. A single photon comes here, it's one path and another path. But to know when the single photon is actually emitted, I have another reference pointer. Whenever I detect a photon at D0 in detector D0, then it means there is one photon which has gone here. If I do an experiment, just one experiment, it comes to this beam splitter, either it gets detected here or here, because I can't detect half photon. One of the detector will click, D1 will click or D2 click. I can't detect half a photon. Then how do I know that photon actually takes a split path? It is going in two paths. So it means that detector here are acting like an observer. In two slit, I said if I'm observing, it says which path it is taking. But observer is acting here. But to confirm that it actually has a wave behavior even in this experiment, I need to send some 10 photons, 1000 photons, or 100 photons. So when I repeat this experiment, and if my detector D0 detects 100 photon, then after I do this experiment on the other arm here, I would have detected 50 photons here and 50 photons in D1 and D2, which means half of the time the detector which has come, photon which has come here, takes this path, and half of the time it goes this path. So any quantum experiments, confirmations come after repeating it. Okay, so there is something, as I mentioned here, the absence of coincidence between D1 and D2. So, which means you will never have a possibility of detecting simultaneously photon in D1 and D2. It will either be in D1 or D2, which means there is a single photon which either takes this path or this path, but there will never be a splitting of photon and half photon getting detected here or here. So particle nature is conserved when you are detecting here. You will either get click here or here. Even if I'm doing this experiment 10,000 times or million times, I will not get simultaneous detection on D1 and D2, which matches with detector D0. So particle nature is conserved because there is no coincidence between detector D1 and D2. But wave nature is also conserved here. How? It means I am getting a detection part here half of the time and half of the time which is here. Now, if I am sending them without measuring and let them to interfere, there are other experiments to do that. Then there will also be a wave behavior which comes to the picture. This experiment and the previous description which I said about wave nature and the particle nature both exist, can be confirmed by this simple experiment. These things were done 50, 60 years before. Okay, so I'm just giving an introduction to look at it. Okay, so there is wave particle duality, which is first point we have to take, and many experiments are confirmed up to this stage. That's a takeaway from these two slides. And photon is either detected in full or it's not detected. It's not detected as half photon in any of the detectors. And another important feature which comes from quantum mechanical systems or from quantum physics is the superposition. Okay, so this is something very one of the most striking and important feature of it. We call them as we represent them in vector notation. If you are not introduced to Dirac notation and Dirac quantum mechanics, you don't worry about it. You might remember vector and you might remember scalar quantities, right? Scalar quantities are 0 and 1. It will be two possibilities, just like there's no direction. But when vector quantities would have direction, it is represented this form, which means a quantum particle can simultaneously be at two places in a given time. This is exactly what happens here. If I'm sending a single photon, until it hits a detector, I really don't know whether the photon is here or not. Before hitting a detector, I can never say whether it is here or not. I have to say that it is in superposition of this path and this path. Only detector will collapse it to either this or this. So that is something which would say. So classical mechanics, in all of our classical system, like there is somebody who wants to take, our car is moving in a path, or I'm walking in a path, I would either have to take one of those directions and I keep moving like this. But quantum system, if I'm not observing, if I don't have detectors, and if I'm just letting, this can be like multiple beam splitters. Each position can be multiple beam splitter. You can imagine like that. So if a photon is there, there is one beam splitter which splits. And if I'm making a measurement, I will always find, do 10,000 experiments, there will always be some finite probability in all this path. So there is a superposition for the quantum state exists, there's multiple possibility of them to simultaneously be present in more than one place. This is something which quantum mechanics gives as a resource for us to think of its application to technology. So this is a classical system where either you go to the left or right or just put one of the path. In quantum system, you can simultaneously explore multiple possible paths. So quantum superposition is the next thing which comes as a very big advantage. Another most important striking feature which comes from quantum mechanics is quantum entanglement. It actually took many years, like decades, for scientists to confirm. Einstein and his collaborators talked about spooky action, where there is something, if I prepare two quantum state together at some point and then separate them spatially, then there will always be some kind of relationship between both of them. So without knowing an idea of what state or what might be, example is a polarization, without knowing a polarization of particle in B, just by measuring what is there in A, I can get to know what is the state of polarization state of photon B. So it's, as statement is here, two carefully prepared photons can be physically separated from one another, and any change of state performed on one photon will instantaneously result in change in another photon, which means today in our current communication technology, let's say I'm talking to you now and the signals are reaching you. These signals are reaching you at the speed of light because these are electromagnetic waves, and we don't recognize the delay which is happening because speed of light itself is very far. But in quantum mechanics, even that is beaten, because if I'm considering, if we were entangled between Bangalore, I'm sitting in Bangalore now and you are in Kolkata, if any information, any changes that's happening here can directly reflect in Kolkata, it means that there is an instantaneous information exchange between A and B, and this happens only because of quantum entanglement. So this is a resource people have for last few decades in lab, they've generated and used it for various applications. So now let's go to let's say think of how these features. Okay, so I will at this point I will stop the introduction to quantum mechanical basics, the phenomena of it, and then try to see why we want to exploit the things which you have learned from sciences. This is the sciences, quantum theory, understanding quantum theory over last many decades have helped us to understand that there is a wave particle duality, which is not naturally observed in classical physics picture, with the way we understand Newtonian mechanics. And there is superposition and there is entanglement. If we know some new science, then it is our role to understand. So this is again, how we started learning about nature and discover. There are many reasons why we want to take quantum physics to laboratory setup. There is a nature. Nature always teaches us. It's not that we are not invented quantum mechanics. Nature itself is contributing to us. So when we learn something from nature, we have some curiosity to explore it to some point, and we understand them. After we understand them, we start predicting and and then we start controlling them. Once we know that we have learned and try to control, we convert them into technology, and then we have a social impact. This cycle of discovery is continuous. Examples are there, like steam. This is very trivial. Even Stone Age, if you go from the way people looked at in very prehistoric days, some small things, fire really led to various, from fire, many things started. We learned to cook. There was curiosity, what was fire, understand them, predict, control them. Today we control fire, and that has led to a social impact. Then steam came, then engine. Whole of our motor system was built from the discovery of science, understanding, predicting, and looking at it. So early 1900s, 1920s, 30s, electromagnetic theory, we started learning about EM theory. It's again classical mechanical pictures, right? It's not a very finite understanding of it. And the moment we understood and started controlling electromagnetic waves, then we have all of our current technology which is in front of us, right? We are talking, we have Wi-Fi connections, we have telecommunications to everything, right? Signals, TVs, multiple channels, everything is there. It's all the way we learn and manipulate electromagnetic waves. Electromagnetic wave spectrum is large. Each and every spectrum has their own advantages just based on their frequencies and wavelengths, how they can interact with different systems. That's all, right? It's an electromagnetic wave of large spectrum. Each wavelength frequencies has certain manipulable manipulations approaches, and then they have certain applications like predicting and control, looking that we know what spectrum is good for Wi-Fi, what spectrum is good for communication, what spectrum is good for military applications, or what spectrum is good for satellite communication. Everything, by predicting and controlling, we learn, and then we are applying it for technology. So that's what initially predict and control happened in early 1920s, 30s, 40s, and then we are reaping its application technology. Now, quantum mechanics has started something more than any of this electromagnetic theory or earlier knowledge. So quantum mechanics is giving us a new tools of superposition, wave particle duality, entanglement. So now people have understood them, started predicting them, and now we are learning to control what we have understood from quantum mechanics. So it means from this stage, humanity is going towards how we can apply it to a technology so that we can have a social impact. So it's not exaggeration. It's neither, trying to, it's sort of like scientific discoveries of decades, and people have a very good understanding. So if you think there has been three major basic discoveries from nature, and we have learned to extract, quantum mechanics will definitely stand as the fourth of in that cycle, which can have an impact for next few days. There might be hurdles, there might be anything, it might not happen. We might have to stop after 2 decades because quantum particles are very sensitive, but the science is there, right? We may not be able to have a very good control the way we want in next 10, 20 years, but definitely in next 30, 40 years, we will have. But that's the worst case scenario. But people are learning to have a good control. But the worst case scenario is it will only be delayed, but it will never be a flaw because quantum mechanics is there, has been tested over time. Okay. So now what these analogies, like for example, nothing is wrong. Newtonian theory is not wrong. Electromagnetic theories are not wrong. Even what we understood from stream or fire, nothing is wrong. It's just that we became more and more accurate in our understanding. Newtonian mechanics still predicts us very well how to launch a satellite, but it's a good approximation, right? It will not tell us how to have a very precise control. A good approximation of any macroscopic systems dynamics, it can be done with Newtonian physics. But the moment we start applying Newtonian physics to atomic systems or smaller systems, then it says, oh, okay, at that small scales, it's not helping us, it's deviating us significantly. That's when Einsteinian physics comes into, general relativity, and classical quantum mechanics comes into the picture. They start removing approximations and start making predictions in a more realistic scenario. You might know, some of you might already know that today's GPS systems work on general relativity. Okay, people never thought general theory of relativity would be useful, or like relativity theory, not gender. I'm not say just special theory of relativity itself is enough. The theory of relativity was not thought of something to be of practical use. It's good. It only talks about explaining things in space, how planetary systems and those dynamics, but they never thought we can make use of it. But today's GPS precision uses general theory of relativity, and that's how we can actually use Ola to Uber or everything, and identify our locations very accurately. And these are developments which even people who discovered anticipated that it will be of some practical use. Okay, and these classical physics approximations have been removed, and we are being more and more precise. And quantum mechanics can actually scale. It explains at smaller regime all the subatomic systems, and we can easily transit to understanding macroscopic also. So now information is there. Today we have information encoding, communications, everything are happening. They're all based on the principles of classical mechanics, classical theory. But if we remove those approximations, then we can call them as quantum information as a bigger picture. So whole idea of our moving to a new technology or improving our understanding of nature, it can be both. You can be a student who are not interested in technology. I'm not worried about technology. My interest is only to understand nature. Even then it's very useful, because if you want to understand nature to the best of your knowledge, best of your capacity, then we need to remove approximations and understand them. So even there, devices which are developed using quantum technology will help us to, so it's all connected. If I build some technology, then I can use that technology again to discover something more deeper. So these are all like cycles of removing approximation and understanding nature. And there can be a set of us, probably some of you would be interested in technology, then your interest would be to see how I can manipulate them and convert them into a useful technology. Okay, so relativity removes approximations that we are traveling at much lower than speed of light. Quantum mechanics removes approximations of dealing at a larger system. So it means that only explains everything at an atomic scale. So quantum information computing, we remove approximations that elements of information are independently manipulable. So we remove those approximations, then we get more precise. We don't have to deal with microscopic scale. So how things are, this was just an example. History of computers, the way it started, the first computers were 18,000 vacuum tubes, and then it was a 2-floor building in Berkeley, near University of Berkeley. That is very, probably today's, even the simplest mobile or like even handsets or the very old generation handset would beat the capacity of these machines which were built in the early stages. And then the invention of transistors, miniaturized, completely integrated circuits are miniaturized, and we have advanced a lot of them over time. So that's the way things have evolved and moved forward. So that is one reason, as I said, the technology, how it has evolved. Another reason, a simple thing which Professor Feynman put up in 1981, he said, see, if computers were invented at that time, there was this stage of computers were done, transistors were invented, and people were using computers to do tough calculations, right? When you say tough calculations, it means that today we write some expressions, we solve solutions, we get them, but there are many complicated equations which you can't solve by hand. We have to go to computers and solve them. So what Feynman said is that computers are used for simulating, right? If I have to simulate nature, then I need to simulate with something which actually behaves like nature. Only then I can do a good approximation, right? I can only compare apples with an apple. I can't compare apple with an orange. So if nature behaves, by that time, by 1981, I was telling, like quantum mechanics was established as a theory. People understood atoms, everything well. So quantum mechanics is a theory which describes nature. But we have computers which follows classical nature, classical behaviors. So that can't do a calculations exactly the way nature does. Then it is some approximation. So if we really want to simulate or mimic what is happening in nature, we need to build devices which follows principles of quantum mechanics. That's something which was an invitation in 1981 to develop quantum computers which follows principles of quantum mechanics. Only then we can simulate nature. So Feynman had no idea about commercial use of computers, or computers should be built because you can have big companies and make a lot of money. So it was his idea was to understand nature to the best of it, we need to have a system which follows principles of quantum mechanics. Okay, so that's this reason. Now I will tell you, this is to give you a numbers just to give you an idea how big a quantum system is an advantage. Okay, first probably we'll just you can just keep in mind the basics of quantum phenomena and how we have removed approximations up to now. What Feynman hinted in this statement. Okay, so this is a number representation of it. If I take atom, right? If I'm taking an atom, just take hydrogen atom. It has only one electron. We can say that electrons can be excited state or a ground state. Okay. Now, atom electrons energy levels are quantum mechanical system. I can represent this state 0 and 1 as ground and excited state. So now, if I want to go and write a code in my classical computers, whatever computers even we use today are classical one, if I have to go to a computer and then say, I need 2 bits, right? 2 bits of information. One to say ground state and other to state excited state, right? This is there. Now, let me take 2 hydrogen atoms, okay? Now, 2 hydrogen atoms, some way, let's not worry about whether such kind of interactions are possible. These are just an example. I have 2 hydrogen atoms and there are electrons which can be in ground and excited. Somehow I make them interact. It can be any molecules, right? I make them interact. Then there is possibility of H2, right? Hydrogen, water bondings happen. So then I can actually have an electron from one atom hopping to another one, right? And want something from this can hop either to go to ground or excited state. So I will have this 4 possibility quantum mechanical states. So it can be in superposition. I said, right? We only mentioned about superposition of 2 states, but they can actually be in multiple combinations, superposition. In both of them, it can be in ground, in one ground and excited, in other one excited on ground, and in both of them excited. So 2 hydrogen atom can be in 4 possible states. So if I just want to mimic electrons, I'm not even mimicking nucleus, I'm only taking electrons energy levels, that's all, ground and excited of 2 hydrogen atoms, right? Then I need 4 classical bits. Like that, if I have just 10 of such electrons of an atom, even you can take any ideal gas systems where most of them are bound, there is only 1 free electron. Okay, we are not even looking at other electrons, just 1 free electrons and 10 of those atoms. Then I can have these possible configurations because there are 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? All of them can be in ground state. All of them can be in excite, 1 ground, 1 excited, everything. Then there are 2 to the power of 10 possible configuration of just 10 electrons of 10 atoms, right? 1 electrons of 10 atoms can be 2 to the power of 10 configuration. And this is the number of classical bits we need just for 10 electrons. Okay. Now, just 30 electrons of an atom. Then we have 1 gigabit of power, classical bits required. We are already reaching a limit of the best computers. Today's laptops or machines we do can't actually do this. They can't actually have so many bits and it doesn't allow us to control. So forget about 50, controlling 50 electrons in an atomic system. These are the limits of classical computers. Even the best supercomputers today, which the world has, stops here, right? Just around 50, 53, 54. They can't go beyond that. So what people do, they do approximations. There are Monte Carlo approximations or various other approximations of doing them in smaller scale, combining them together in parallel process, put them. So those approximations doesn't give us a good predictions of what is the final state of such kind of atomic system. So forget about all complicated systems. Now there is an example here, right? These are all our day-to-day. You might have heard of all of these names, water molecule. To represent water molecules, to do a proper simulation to understand how the dynamics of electrons are happening, electrons or nucleus are happening. Even I'm talking only of electrons. We are not even looking at in detail. We need 10 to the power of 4 classical bits to simulate them exactly. Understand how the water molecules come. Quantum bits, we only need, so because when I say quantum bits, which means they are exactly mimicking like this quantum state, 10 quantum state itself is enough to have all superposition. So if I'm using a quantum system itself, not the classical here, so this classical systems, but quantum system, it means that just a 50 controllable quantum systems, if I can engineer them, then only 42 of them is enough to mimic ethanol. But a classical bits we need is 10 to the power of 12. Coffee, just a coffee, we all drink coffee, it needs about 160 quantum bits, but no current existing supercomputers can actually simulate them. Penicillin, it's a medicine, right? We all know the penicillin injections we get. And today, no exact simulation of penicillin molecules are done. It's all good approximation. So, which means that if we discover quantum computers which can do a good simulation of all of these chemical complexes, then our drug industry or all of the medicinal things which we are developing, what is the configuration of medicines, there are a lot of approximations which are going in to define what are the chemical complexes today for the best drug. In that approximations, we are making some errors, so which means that we are only approximately addressing, and then of course, most of the medicines are working. Then we talk about some side effects, which means that there are many chemical components which are really not useful, but our approximations are giving them as a solution, and that's how the drugs are designed. If we have a very good predictions and removing approximations, then we really don't need to be consume unwanted chemical components. Might be only a precise chemical components is enough, and quantum computers can help in simulating all of those things. So we can see here many things in our day-to-day life we can't understand using classical systems. So again, these are other simple classical examples itself. I would think probably since the time also would become a concern. It's not just the chemical complex problem. What I was trying to say here is that even a simple problem of how you do a seating of 10 people, right? And if number of seats are there per person, and what is the possible configuration of making them align and then sit? There will be so many possible configurations of them. But if I want to say, oh, A and B of that 10 people sitting together, what are the possible configuration? What is the solution to say that these two are sitting together in a third row or fourth row, whatever it is? Even optimization problems can't be done in a classical system explicitly, and quantum computers can help because it can allow us to have a superposition of multiple possibilities and then the solution to them. So again, this is an example which is there. I would probably quickly, this is a quick flash. Nitrogenesis process helps us in farming fertilizers are developed at, using these nitrogenesis enzymes. Okay, today's fertilizers use them. And then we define the components of what is a good fertilizer for our agricultural. There are many things which we don't know. If this is a combination of Epr protein and then things which goes in this nitrogenesis process, today we have been able to only exactly simulate F cluster in classical computers, and the rest of these things we have not been able to simulate PM clusters. We only have a rough approximations of them. So you say this is 2014 paper, and even today we don't know how exactly to simulate them. So in fertilizers, configurations of fertilizers, there's a lot of approximations which has gone to look at the best to understand nitrogenesis and the component of it. The same with photosynthesis. Okay, so there are, even to understand something in nature, this is a complex. You don't have to worry about details of it, but I'll tell you just what important is. Nature follows some quantum processes. These are there are some algae deep in the sea, at 5 kilometer depth. Okay, there is no chances of light falling in them. The light comes from nature, something from sunlight which is entering the surface of the sea. It's traveling 5 kilometers deep into the sea. One photon in a day might be, right? Or in one photon in 2 days enters the surface of those algae, which are this chemical form. They efficiently use that to convert them into an energy in a reaction center, and they're surviving. So we have not been able to understand how exactly, and these are all like quantum processes which is happening in nature straight away. If we understand how exactly it is converting one photon which is entering them into an energy and then surviving, if you understand them well and model them explicitly, then today solar system, what we call solar panels problems will be solved. The people are building solar panels and they're only 20% efficient, 18% actually, 18, 16. Laboratory people have achieved a good 30%. If we understand how this FMO complex converts one photon, which is something efficiently to them, if we model them, mimic them, then we would have solar cells with 80-90% efficiency. That's why we have to learn something from nature, understand the quantum mechanical process, build another quantum system which will mimic what this nature does, and that system can be used to develop a better solar cells in probably next 10-20 years. So these are things which people never understood how the photosynthesis is happening efficiently, right? But there are some partial understanding from the last 30-40 years, partially they are solved. And this also is one example where recently, it's only like last 8-10 years, people understood that quantum mechanics is playing an important role. Nature is actually following some rules of quantum mechanics to convert them efficiently. So mimicking them would help. And people have done some progress in experimental mimicking to some extent. So there are, as I mentioned, some of these problems. There are a whole lot of problems which can be classified into different categories. Problems from nature, problems like optimization, factoring, factoring large numbers. So some things can be addressed in polynomial time, and some things we really don't know. We can do it in polynomial time, and some of them we don't even know even whether quantum computers can solve. But what we knew currently, all of these classical computers could solve many of problems which are polynomial in time. There are many problems which we can't solve, and these belong to this category, like factoring. I don't know whether I have a slide here, but I would say if I'm given two factors P and Q, and then say find out n, which is P cross n, it's a very straightaway problem. If I give you a solution, you multiply and you create a large number. But if I give you a large 10-digit number and then say, please find out prime factors of them, right? P and Q. It's an hard problem. You can't do. It's not easy with any resources because it has to explore all possible configurations. And people are using that as for our secret keys. For example, your PIN, ATM card pins, and various other things are using factoring as a part. It's not easy. No classical computers, best computers today can factor them and then break your pins and then hack your systems. But quantum computers can actually break them, and quantum computers in principle can actually solve many problems which are called as NPR, non-deterministic polynomial time solvables. Okay. We don't know whether quantum computers can also solve these things. People are working on understanding them and looking at it. Probably in 10 years down the line, we'll have a better understanding. Okay, so there are a huge set of problems in nature. It might be chemical complexes, just optimization problem, which quantum systems, quantum computers can solve. Okay. So there are various things. I'm just like flushing them together. Again, miniaturization is one of the things which said, for example, from the big two-floor quantum computers, we have come to integrated circuits. If I'm start making them smaller and smaller, then we said uncertainty principle comes into existence. We can't build devices like that. So quantum mechanics is taken into consideration. You want to miniaturize, and there is a computational power. I gave many examples here how quantum mechanics will give us a computational power. And then there is, I'm not touching this, but there are the way whole security aspects can be solved using quantum mechanics, because the moment somebody makes a measurement, we said it collapses the wave nature. If you're not measuring, then the interference pattern will be there that keeps your information secret. And over last 20-30 years, many laboratories in the world can control atoms, protons, electrons, spins. So once we have learned to control them, we can build a processor based on that, which means you can build a system where there is an input and output. Okay, so now I'll try to just give some examples of things, basic idea of building a quantum system. It can be quantum computers or any quantum technological devices. In any classical information processing, we have these two systems, right? Binary system. All of our information today are binaries. We get it in form of zeros and ones. We code them, everything like alphabets are coded in forms of zeros and ones. This is classical bit. But if I'm changing it to a quantum bit, the moment we go to quantum systems, then it's a vector representation. It can be represented like the 0 and 1. It's just a matrix which I was mentioning of representing in a state. So this becomes your computational states, unlike 0 and 1 in a quantum system. So now this state is physically represented for a photon. For example, if I take a photon, I can take polarization. You can have an horizontal polarization or vertical polarization, right? Or any degrees of freedom. It can be split into, there was a beam splitter, I send a photon, it goes into two paths. One path can be encoded as 0, other path can be encoded as 1. So now I can encode photon as this 0 and 1, and that will be our quantum bits, unlike this. And then electron, it can be spin up or spin down. They can be in superposition or spin up and spin down. It can be an atom itself. For example, I mentioned hydrogen atom, but there are ideal gases, many ideal gases where people can control whole atom and the electrons in them will remain stable. Only one free electron will be there. We can actually control them, manipulate them using laser sources. People have been doing that for decades now. So two energy levels of atoms or ions can be used to control and create such kind of states. So the classical bits can be replaced by quantum bits using these systems. So it means that I'm telling you a building block of quantum system. You want to build a computer or you want to build some quantum source of light which can be used for communications or various of those things, we can use any of those systems. And that will have a superposition. For example, I can use some rubidium atom, for example. It's just an example. People use rubidium atoms to control. Okay, so there is some electron. You can change energy levels of 10 rubidium atoms together, control them, and you can mimic some chemical complexes which are of 10 atoms. So because here you can control them, right? How they interact, and you can mimic and get the results out of it. So that has been looking at. And electron, this is just a mathematical representation of entanglement, right? If I say if the particles are entangled, one of them is 0, the other one also will be 0. If I make a measurement, it collapses to this part or this part. Okay. interference is there, and measurement collapses. All these things are now resources people have learned to control. So using these resources, today in front of us, we have entanglement, which can be both short and we can understand both subnuclear system, a cosmological system, and explore how complex quantum systems can be looked at. And how smoothly we can go from classical to quantum. These things which we don't understand them very well, but both the technology and our knowledge of quantum information, encoding them, is going to help them more. Even there are many things in nature, how the information processing is happening in biological systems or in black holes. We really don't know them all. But if we have a good quantum controlled systems, we can mimic those behaviors and try to understand them, in a better accuracy. Because there are many big questions here. So I think in the next few minutes, I'll try to give you one simple examples. In fact, we are working on that in collaboration with some groups in Maryland. We developed an algorithm to simulate, like I said here, to understand biological system or black holes, we use one system to simulate another one. Okay. A simple example here. You might have heard of classical random walk and probably a drunken man's problems, which is I toss a coin. If I get head, I move to left. If I get tail, I move to right. Just a simple example. If there is some monkey here, he wants to find a banana, how difficult it is, how many times he has to do this experiments to find. Okay. And it says classical random walk problem persistence. Now, this is similar to our Google search, right? You are all used to, you search something and that actually does that. It's a random walk problem which tries to search for information in the network wherever it exists, where when it finds the information, it comes back. So it is an algorithm. Classical random walk is an algorithm which has been widely used in our computational systems. Now, if I'm replacing that classical random walk algorithm in computers with a quantum algorithm, something like quantum walk, which means simultaneously the walker tries to find out all possible with one go. And even only one time, just one time evolution he does, with some finite probability, you would be able to find his destination, right? Unlike the classical system here. With some finite probability, experiment has to be repeated, but it still gives you some finite probability, even in the first go, to find what is. So because it is evolving superposition, there is something which is happening. And I will skip the way it's represented mathematically to describe them. Like I said, you toss a coin, go to left or right, right? If I'm writing it in a mathematical formalism, you can call, if I'm making a spin electron or a photon to do that, it can be polarization or spin up or spin down, right? And this is a position of this representation. So it can be in superposition of both spin up and spin down simultaneously. And a coin will be here different. Unlike head or tail, there is a possibility of going simultaneously to left and right. So it has to be a matrix because superposition of two possibilities will happen. So it means this is just nothing, complicated. It might look a bit complicated to some of you. It means if it is spin up, it goes to left, j to j minus 1. If it is spin down, it goes from j to j plus 1. But if it is together in superposition of spin up and spin down, it simultaneously goes to both left and right. That is what is happening in this sphere, right? It is simultaneously going to left and right. So that is only a mathematical representation of it. See, but that mathematical representation gives you a significantly striking feature, right? This is what the probability of a classical random walker happens, even if it does them 10,000 times, where he goes and identifies. If some object is far away, he will never be able to find them from the origin. It's just like the way even our information, if some informations are not about distance, but it might be various parameters, the way they describe is very different, but you are only exploring this region using a classical random walk approach. If I'm using a quantum walk, then it is exploring all possible paths, and then it's a quadratically faster time than a classical one. So this was quantum mechanical principle, but quantum physicists never gave importance to it when it was earlier discovered. But computer scientists who were looking at algorithms were developing saw a very striking feature of this quadratically fast, and many quantum algorithms were developed based on it, quantum search algorithms. So they are all ready now. When there is a quantum system which will be developed in a large scale, these algorithms will be applied to do the search and look at it very efficiently because it's spanning faster, right? You see a dramatic quadratically faster spreading in position space. So it's one of the striking features for an algorithm point of view. Now, these algorithms are not just useful for computational tasks. It also helps you to model quantum mechanical systems. So what is happening here? Why do we get this quadratic faster spreading? It's because it is exploiting two features which we introduced in the earlier slides, right? Superposition is something which is exploiting, and interference. That's all. It is exploiting the possibility of being simultaneously in two states. And when it is evolving, there is a superposition experiment. Right? You can now connect this description to an interference. Instead of just having two paths, first I will have two slits, then the next time I would have 3 slits or 4 slits, then next time I would have multiple slits. But I send the same photon. So they all, at each stage, they start splitting and they interfere and give you some complicated interference pattern. And that is helping you. And that is giving you a quadratically faster spread line compound. And people have experimentally done these things using different systems. In many systems, they have developed and they have looked at it. In fact, we now used this algorithm not only to look at algorithm side, but to mimic nature. If you remember, I told you, right, Feynman's idea was something is happening in nature quantum mechanically. We need to learn to simulate them. So we are looking at developing algorithms to simulate nature. It's not to simulate search problems, but to say simulate nature. This is some standard neutrino oscillation problem, which is happening in nature. There are 3 flavors of neutrino. When there is change of flavors which is happening over time from one to another. Not have to look into details, worry about it, but using the same quantum walk algorithm, one can simulate the oscillation of probability from one flavor to other. This is exactly what experiments observe. But we have an algorithm now, which based on quantum physics principles. So when we have quantum computers, these algorithms can be applied to simulate more complicated behaviors of neutrinos and everything, which classical computers can't do. This is another implementation, realizations which we have tried is, for example, nature, right? We have curved space-time. We mentioned black hole and various other things. Now, I want to mimic curvature and I want to have a quantum algorithm so that I implement it in concept. For example, what it means is I take atoms and then try to change the states and look at it so that the output result would be something what describes a curvature in space. So in a laboratory, in a flat surface, I can mimic curvature in space. This says the moment or rather the way the particle moves, it can Dirac particle, relativistic particle moves in a curved space-time. But these simulations are done using quantum algorithms, which can be used on any in any flat surfaces, which will mimic quantum. So these are done with small time scale and using single system. So it's only in principle proofs. It's not dealt with more complicated dynamics because classical computers can't do. Because quantum algorithms were rewritten such that it fits classical system to show that if we have a good quantum mechanical system, these things can be efficiently simulated. So these were all done to show in recent times. And then I'll skip this factoring and algorithms part because we're running short of time. And algorithm today, people don't know which is the best systems available. There are many hardwares people are developing across the world. Earlier versions was NMR spins, but they are not very efficient to scale. Today's leading systems are these two, ion trap system and superconducting. IBM and Google are working on a large scale of superconducting systems. There are other companies, Honeywell in collaboration with University of Maryland, are trying to build ion trap systems, which are good candidates for quantum computers. And various other systems have also been explored. Nobody knows which would be the ultimate one. It can be a combination of them, but every system has their own advantages of dealing with it. And okay, I'll skip this thing. This is just a molecular. When I said NMR systems, what they do is they take some controllable molecules. This is one example of F16 fluorine atom molecules, where it has carbon atoms and hydrogens. You can control their energy levels, and it can be used to mimic some other systems. These are the ion trap systems, where this is just a base where 53 ions are trapped and they are controlled. So this is the time, like each time when it's bright light or off, or the combinations of them would tell you what is the computation process which is happening. So this is an example of 53 qubit quantum processor using ion trap system, and this is a Maryland's device that they developed. These are the superconducting circuit, which is slightly different. But all of them are bulky today, but we should not be we should not see it as a disadvantage, right? Because first time classical computers was a 2-story building in Berkeley. Compared to that, this is a lot more better. This is the quantum computers where actually the chips are not too big, complicated. It's a very small thing inside. But here, these are all the circuits connecting to them. The superconducting circuits where current flowing in two opposite directions are treated as two states of quantum system, but they have to be controlled in a cryogenic system. It has to be, even small variation in temperature will make them lose quantum behavior. So that is making them bulky, connecting, wiring, and all of those things. These are the IBM machines which have been built, and this how a chip would be somewhere here, a small portion of it, and these are all the control system for it. And this has been looked at it. So people are looking at. So what is another advantage of quantum processors compared to classical processors? It's a one simple analogy here. If I have to double my computational power in classical computers, right? Today we have a chip, we say it's a memory, it's computational capacity, so and so. If I want to double, I need to multiply the chips. In fact, I need to add 2 chips to have a double computational capacity and power. But in quantum systems, I just had to add one additional quantum bit to that processor. It doubles its power, because each one qubit you add can be entangled into all of them, and the power immediately becomes double. That is an advantage. 16 qubit device, if I'm making it a 17 qubit, its computational power has doubled. If I have 200 qubit quantum computers, if I make it 201 qubit, its computational power becomes 2 times its capacity. But that will never happen in a classical transistor systems. You need to add them to power. So these are all the advantages which people are anticipating. But today, these are noisy devices. They are like 16, 20, everything up to now some 53 qubits have been developed with the control of each qubit. They are noisy. You can't do all processors. Quantum systems has to be very nicely guarded from environment. Even small environmental disturbances can disturb them and lose quantum behaviors. So there are a lot of hurdles in the process, but things have improved dramatically. For example, 10, 15 years when I was doing my PhD, 15 years back, we never thought that in next 10, 15 years, we would actually reach this stage. We were only studying it as a curiosity and how to do some research, probably as a foundational part of it. But we never thought technological advancement would be so fast in this area. So we don't know how it's going to be next few years. It can be dramatically changed. There might be hurdles which we'll understand. But today, people have what we call noisy intermediate ones. These are not exactly commercially available devices which can be of significant practical use. Today's devices are helping us to test, build them, test, improve. Right? It's in the research and development stage because currently the available what we call coherence time, which means when up to what time they still remain quantum, when the environment is not destroying them. These times are very small. So people are improving on them, and connections. How do you build the circuits, so that you can do operations? People are improving on many of those things. Error corrections, big issues, but people are looking at it. But what these are the predictions when you're looking at probably when we say this is a number of years by the time we can look at it, probably next 5 years, many quantum chemistry problems. I looked at some chemical molecules, right? We need some 50, 60, 100 qubits. So if people have a good controllable 100, 200 qubits, many quantum chemistry problems, which can have implications in drug industry, can be done in next 5 years. Some optimizations problems and heuristic machine learning approaches. In next 5 to 10 years, it's possible. But to get into a cracking of Shor's factoring algorithm, what I said, factoring problems, that is the security which we are talking about. In next 10 to 15 years, these are predictions looking at the way the research is happening, not astrological predictions, scientifically motivated estimations people have made. Shor's factoring algorithms can be implemented effectively in next 10 to 15 years. If that happens, which means all of our security today, which are encrypted in factoring forms can be broken in next 10 to 15 years. That makes it big. And so next 10, 15 years, we probably would have a good controllable quantum system. I think I will just take 2-3 minutes and conclude, and probably we can have some discussions. This is just, you might not have to worry about much about it, but just to say that even with simple 5-qubit machines, we worked in collaboration. This is quantum walk algorithm. So we developed, looked at it, and we built a circuit, how quantum circuits has to be built. This is like, 1, 2, 3, 4, 5 qubit machine, and what are the operations you need on them. These are all like laser which controls ions energy levels. We convert them into it. And then when we developed, you build an algorithm mathematically, you convert them into quantum circuit, and you try to identify, is there a quantum system currently available from which we can implement it. So we collaborated from the University of Maryland group, and we could implement simulation of Dirac equation. These are not anything dramatic, which means I can actually, in my computers, I can simulate hundreds of steps of Dirac equations, because classical computers also can do Dirac particles dynamics, because they are not very complicated, it can do. But in principle, we have to show that even small scale quantum computers at every stage, it is implementing quantum operations and it is doing controllable. So this is the experimental results which we got from Maryland's ion trap machines. They currently have the best machine in the world, but we only chose 8-qubit machine in their system because coherence time, you can't do. It's not just about having number of qubits. Google recently had 53 qubit. They said we have broken some world record, but it doesn't do a very useful operation because noise is disturbing it and all of those things. We wanted to have a noiseless operation, so only 5 qubits. Number of gates like this, some 80 to 100 gates were done. We could mimic what Dirac equation will do, or Dirac particles actually in nature would do, using a quantum system. This is an experimental result, and these are the predictions. It matches. It only said that over time, if I have a good control over quantum mechanical systems, then we can actually do more complicated relativistic quantum dynamics on a quantum computers. In fact, these are the things which you might have heard of. Large Hadron Collider, which is in Geneva, international collaboration, where there are also many people are working on developing quantum algorithms and keep it ready so that you can actually simulate them, and it can save millions and millions of dollars. Today, people are directly going into a Large Hadron Collider and then doing experiments. They're very expensive. Building things takes millions of dollars from international collaborations. And we don't know whether what we want to do is correct or not. So if we have some simulations, predict them in advance, then we can actually decide precisely what experiment to do. We don't have to do a lot of other peripheral things to do. So quantum algorithms in long run probably can help us.
So is there any connectivity problem?
I guess so.
I think, sir. I think,
Hello?
sir. So,
Yes, sir.
Hello?
Yeah.
yeah. Okay, sir. Yes, sir.
Please.
Hello?
Yeah. We can hear you. Can you hear us?
Yeah, I can hear you. Sorry, I think I was in the last slide and there was some power problem.
No problem.
Just let me
Please go
share
on.
the last slide. Okay, you can see the screen?
Yes.
Okay. Yeah. So I would conclude at this point. Probably we can ask questions, and that's.
Thank you, sir. Thank you for your very informative and nice presentation. And what we have found in today's talk that in spite of there is very heavy rain outside in this part of our West Bengal, participants are still there. So they have asked 5 to 6 questions. So can we ask one by one to you, sir?
Yeah. Please. Yeah. I'll be
Okay.
happy.
Okay. So let me take the first question asked by Saurabh Natta. His question is also related to very basic things. Why quantum entanglement characterized as a spooky action at a distance?
Okay. So when I was in one of the pictures, I showed that if I carefully prepare and separate them, right? So if there are two different destinations, I'm probably we're talking from Bangalore to Kolkata, right? Are two different destinations. If I'm changing the state somewhere here, instantaneously there is some information of what has happened at my end. So that is spooky because initially now it probably the words are changed. Einstein called it as paradox at that stage, and they were thinking of hidden variables. Today, we understand how entanglement is happening in a system. So that's normal. We can't probably have to consider it as spooky at this point because we understand them better than in what it was. So that action without any reason or any intervention of us to do that, we are getting an information. And for that reason, they use the word spooky. Paradox was also used paradox for a long time. Even today, many of them use because they thought there is some hidden variable we don't understand. That is why this spooky action is happening between those two. But we know today, people are generating entangled state in using various different systems. Once they know how they are generating, and we know how these contributions are coming. So this hidden variable theorem and all those things have been addressed to a good extent. We didn't discuss explicitly, but I had this slide where I said, you can have a photon of some, for example, one can take, this is just an example which people are doing in all around the world, 410 nanometer laser light. If it is sent to some particular medium, it can split. One single photon will enter into an atom or some material, right? When it enters, it excites to some higher energy. When it excites, it has to de-excite to a ground state. So instead of doing it to one go, it can split into two. There might be some intermediate energy level, it falls there. Whenever there is a decay from one energy level to another, it emits photon. If that decay happens twice, then a single photon of high energy, which is observed in changing, when it is decaying, it takes two different routes and emits two photons. But it can emit in two different polarizations. So that coming from a single photon, two photons are coming of different polarization, and they will have a single origin. Now these two photons can be treated as entangled photons. And people are consistently generating it and using it for communications. The same way it is done in various other systems. So that spooky is coming because we don't worry about, we say that simultaneously it is generated, we don't know how it is, but when we say, oh, some change is happening in one and the other is reflecting, they use this word.
Okay. Thank you, sir. Probably the next question, which has been asked by Orkun Ghosh, has already been answered. His question is, what is actually quantum entanglement? Sir has already explained in the first question, and why, where it is application, means what is the application of quantum entanglement? So.
Okay. Yeah, so today I will give one simple example which has been very widely used in many technological applications, communications, right? For example, if I have today, I'm communicating or I'm exchanging. So there is some medium for me to exchange keys. For example, I go to my ATM machine, I enter PIN, and that PIN is getting physically transferred either via our wireless network or wired network in some way, and it is getting verified. Only then I'm getting an access. But that is happening at the speed of light. So this information from A to B needs a medium for it to transfer in all of our current communication approaches. Either you are using it for security or for communication. That medium is needed. But if I'm having an entangled one, like for example, I prepare two photons initially. We don't talk about any exchanging things. and I send it to two different destinations many kilometers away. Now I can exchange information instantaneously using entangled source without any medium for it to transfer, which means that then where is the chance of somebody hacking you in path? Hacking is happening, interception is happening, everything is happening only because somebody is coming in the path of your information and trying to steal them. That can be completely avoided using entanglement. So it might look sci-fi version or a movie versions of what I'm saying, but exactly people have done this experiments. China and then Vienna collaboration, they did some between Beijing and Vienna, they exchanged this kind of information using satellites, right? So entangled source was exchanged before. So in advance, they have to exchange entangled photons, some 70,000, right? 7,000 kilometers actually between Vienna and Beijing. They exchanged, they transferred image of, I think, Einstein from A to B by encoding it. Nobody could intercept because these keys are exchanged using entangled source. So the need of medium is not required at all. This is only one example of using entangled source in communication. So I said, I also, in the talk, I was mentioning about chemical molecules and various other things. There also entanglement plays a role, but I have given an example because I have an idea of various applications which entanglement can have and secure your information.
Okay, so thank you. So the next question is asked by our student, BSc student Deep Chaudhary, sir. And he is actually asking about the first few slides where you have shown one beam splitter is there, interference pattern is basically going to be
So it's already answered. So BS is beam splitter. Okay.
Beam splitter. So the question is that it is a glass substrate or something else. So it is very trivial question, but okay. So let us go to the next question. But I think speaker is now not present. Again, I mean, he is also suffering from some connection issues.
Yeah.
Let us wait, and I think Tamal sir, can we take two questions? I think.
So he's back. I think. I mean, speaker
Okay.
is back.
Okay. Tamal sir.
Yeah. Okay. So our speaker is back. So maybe
it's raining in Calcutta, but
yeah,
raining in Calcutta, but we have power interruption.
yeah, maybe some kind of entanglement is going on.
So another question that has been asked by our student. So Chandrasekhar sir, are you? Can you hear my voice?
Yeah, I can hear. Please, yeah, go ahead.
Okay. So Saurabh Rudra from BSc Physics, he asks that, sir, for quantum teleportation to take place, Bob must know Ali's measurement outcome, which in fact prevents quantum teleportation and prevents it to take place faster than speed of light. So is there any development of new methods by which this problem can be tackled?
Hello.
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 Yes, sir. Yes, sir.
Hello. Actually, quantum states. So there is
your voice is breaking, so
Yes,
maybe
voice
there is serious
maybe.
problem with the network. I mean, so
no, I think there was the power interruption, and I'm using the mobile.
Okay, I understand. So now your voice is okay, I think.
Now your voice is okay. Fine.
No, no. Wait. He's not there. Yeah, he's there. Okay.
Okay.
Yeah. So you are on you're on mute, I think. I mean, so maybe he's unmute.
Yeah. I think the teleportation has slightly more intricate way of doing it. The measurement is not done in a complete state. measurement happens, there will be one reference ancilla qubit, what they call additional qubit, and that is entangled with another system. So you make a measurement on that alone. So you are not collapsing a full state. You can collapse only a subsystem of it without collapsing the state you have teleported. So in that way, you are always. So what you actually do is that you take a bigger system, make a measurement in a smaller part of it, and the state system or a state you have to teleport is retained intact. So in that way, the collapse is not disturbing a teleportation in full. If probably that answers I hope it answers the question.
Okay. So, Tomal sir, just we take last question.
Okay, sure.
So this is asking by Shivam, and what is his question is that, can we also have a possibility that a classical machine algorithm can come up with a very strong encryption which even cannot be solved by a quantum computer? That means he's asking that what is the...
No, yeah. I think this is not this is a very important question in the sense, many of them do think that, there are Short's algorithm in quantum mechanics, quantum information, which breaks RSA cryptography. So there are not many algorithms. So there is one new area, one field of research, which is called post-quantum cryptography. Okay. So in that, people are looking at it from computer science perspective. Can we develop algorithms which can be guarded even from quantum computers hacking? So they are looking at it, but these are not something which can be absolutely answered at this point of time. If people develop an algorithm and then say this can't be hacked by the current quantum algorithms, somebody can develop a new quantum algorithms to crack that. So this is complete. It is a parallel evolution process. Post-quantum crypto field itself, people are not studying quantum mechanics. They are only building classical algorithms to safeguard quantum mechanics. In parallel, people working in quantum algorithms are trying to have an algorithms which would crack. So in that way, you are increasing the bar at both the levels. In fact, most of the nation security, either in India or various of them, they are investing quite a lot on post-quantum cryptography, because everybody may not develop quantum computers first. Whichever country develops quantum computers first, an efficient one, they will be at an edge of breaking our security. So they need to have a better algorithms to safeguard our information. So they are investing more on post-quantum also in parallel with quantum computers. So we can't answer these questions absolutely, but there's no room to believe that this is not possible or this is not. It's a road to explore.
Okay, so thank you, sir. Thank you for your very nice presentation. And we have really a very good opportunity that we have got, so that you have learned so many things. From
Shahrukh?
Yes, madam.
Can you ask one question to the speaker? No, you're
Yes,
out.
madam.
You're out of time.
No, I am
No,
okay.
no,
I
madam.
can answer. Please.
Okay.
Thank you so much, Professor Chandrasekhar, for such a nice presentation. As you have just pointed out about the Epr paradox, I just want to just please, if you can say more lines about Epr paradox and whether it is resolved. What is its status nowadays?
No, okay. As I said, I think in answering one of the questions,
Yeah.
it was Epr paradox was something which hello, yeah, you're here. Oh, yeah.
Yeah.
So,
Yes.
yeah, it's not a paradox now anymore, because we have been able to understand how entanglement is happening in the system and at what level one can have control. So paradox came because they believed that there is some hidden variable which the current mathematical structure or a quantum mechanical formalism was not answering. But in like 1960s, 1970s, 80s itself, people resolved it to a very good extent. It is no more a paradox, because we know how entangled states are generated and what is causing. When I said in communications, there is A and B, people have done experiments for 7,000 kilometers between Vienna and Beijing. Now they can control them. They can control them because they know what are the parameters which are going in generating and controlling entangled state. So if it had remained paradox, we don't know how to have control and why this exact entanglement is happening, why collapse in one is giving information of other, people could not have used it as an application part of it. So from that point of view, if I'm answering, it's resolved. But what was considered as hidden variable and how that has been answered, probably it would need a bit more mathematical way of explaining, and which without a board and those things, it becomes a bit difficult. I hope I could at least give a first level answer to your question.
Thank you so much. Okay.
Thank you, madam.
May I have one very, I will take only 1 minute, sir.
Sure, sir. Sure, sir.
So, Professor Chandrasekhar, one thing, just then can we say that quantum information over classical is basically reduction in dimensionality?
No, not completely. How do you, okay. So reduction in dimensionality, it means that even if I increase the dimension of a classical system, I can't mimic entanglement.
Okay.
So that is the problem here, right? Many things, for example, even collapse or being in superposition simultaneously, I can't mimic them.
Okay.
So it is not just a scaling factor. Scaling is one of them, but then because of that issue, we tried, there are, again, I just gave a number of classical computers need so many bits to mimic a, molecules of some dimensions. So that number will give you those possible states, the equal possible states, but coefficients of how they are entangling and the normality are much more difficult to achieve in classical systems. So algorithms has to be written forcefully. You have to put those things in hand. So it is not just a reduction in dimensionality. It's only a part of it, but it's more to do with it. There is no classical system which can mimic entanglement. No classical system can do the superposition and measurement together, because as I mentioned, there is interference of waves and those things happen. Even electromagnetic waves, we write them in superposition, right? Circular polarization, superposition of those things. But they are not quantum mechanical because collapse does not happen there. So superposition in together with measurement is another unique quantum feature which no classical system can do. It's even if I'm giving a huge resource. That was a statement which Feynman made, where he was telling whatever might be, whatever best classical system we have, it can't mimic quantum mechanical system exactly the way it does, because these features cannot be mimicked in a classical system. They can only be approximated in a classical system. So he never worried about scales there. He only worried about the physical phenomena there.
Okay, thank you so much, sir.
So I have also one quick question. So that is, how do you treat quantum entanglement at the, at the Hamiltonian or Lagrangian level? You introduce some kind of interactions, or you put it by hand somehow?
Yeah, there are many. It depends on the system level to system levels, which are looking. In fact, you mentioned that we are setting up a lab in IISc now. We are building entangled photon sources. So we are developing there. Where using photons, you use a different approaches. Where, as I was mentioning, you send a photon of 405, and then you send it into a unique crystal. The crystals have some particular molecules. They're made of some particular compositions.
I'm talking about the theoretically. How do you address it?
Yes, exactly. Theoretically also, that's exactly what it means. You are looking at a Hamiltonian interaction, right? So when we say Hamiltonian, there is an interaction of photon into an atom. So then you write down an Hamiltonian of an atom, and you write down an Hamiltonian interaction Hamiltonian of photon and atom. It's atom-like interactions, right? So there you are looking at the Raman transitions which are happening, stimulated transitions which are happening. So that way you are solving it at an Hamiltonian level. You have an interaction Hamiltonian, you have a systems Hamiltonian, and the interactions would solve and they create output state. The solutions of them would actually give you an entangled state of it. That's one way. That's for atoms. People also do that with atomic systems. In atomic systems, you take two atoms itself, you introduce interactions between two atoms, might be in optical lattices or something. Again, that is done in a Hamiltonian level. You have an independent Hamiltonians of two atoms, interaction terms are introduced, and those interaction terms are something which is a laser or force or some what we call Rabi oscillations between those things are controlled using an external source from an interaction term, and that will create again a superposed output states on a system together. So that's how it is done in most of. You're right when you say Hamiltonians are there, but then interaction term will come into the picture to create entanglement.
So that arises naturally. I mean, you don't have to put a
yes,
special kind of interactions.
True. Yeah. So that's what I was telling. That's those kinds of things. Even Jens coming Hamiltonian approaches when they look at atom-like interactions. How it's what kind of interaction term you are introducing between those systems plays a role. So that's a very precise way of interactions has to be done to create. So they have done that, and now they also have a very good control of generating different kinds of entangled systems by say these are the kinds of interactions which you can introduce to entangle in these possible ways. Yeah, that also resolved this hidden variable problem to previous questions, right? Because these things are there. We know what to be put in to create those states, and that was not known during those days, 1940s, 50s.
Thank you.
I think someone raised hand. So, but another question. Can I?
Yeah, sure. I'm okay. I'm fine.
So it was asked by. It has been asked by Pratik Others. His question is, sir, you have considered Copenhagen interpretation. How would be the scenario if we consider many world interpretation, MWI?
Okay. No, so many world interpretation has not been used for quantum information and computing procedure at all today. People who are working in quantum information and computing, only because we are going by the experimental evidences which exist. So what interpretation fits experimental observations to the best, because we have to look at the technological side of it and what are the practical side of it. So that many world interpretation is out of practical consideration for the current. People are doing some experiments to establish experimental feasibility of many world interpretation, but that has not happened. Okay. So Copenhagen interpretations is very well connected for a practical scenario, matching up with an experimental observation at every stage. So that's what is being used for applications now.
Swarup, yeah, there was another questions from maybe Kaushik Kanunsa. So let's take it and then continue. Yeah.
Oh, okay. So Kaushik, can you please ask your question? Please unmute yourself.
Good afternoon, sir.
Yeah, good afternoon.
I'm audible.
Yes,
yeah.
So my question is that, like photon, it has a different kind of property and all. So where will we place photon in our modern world, and can we have a different periodic table for photon, and can we make a different branch out of it and explore the world of photon?
No, when you say photon is not a element, right? It is just an energy form. It's a light which is coming. It's one of the most basic element of our nature. So photon is also unlike electron, or which kind of combines and there is some charge into it. Electrons, protons, they form. So if you look at basic elements, electron, photons, and the quarks are the one which are forming what is the system. So when you say periodic table, which means that photon is not actually interacting with anything. So photon is not contributing for an atomic structure or to make any elements of its own. So I don't know when you say making a new periodic table.
Sir, I was just saying it because if we consider the other universe around or other galaxies, they might have a different property and different structure with photon, and there are several things which are within photon which we don't talk about much, and we hardly know about it. Now when we explore the world of photon, and when we explore this energy level of photon, it changes and it has different property at different stage, and it varies, sir. So that is the thing which I was
I think when we say different properties, we need to be a bit more explicit in those things, because today photon, in this talk or in a basic levels, we only talk about polarizations, right? We control polarizations of photons and we handle them to applications. But there are other degrees of freedom of photons. We call it of orbital angular momentum. You can squeeze laser light, you get quantum states. So these properties, people understand the way you can control light element particle is photon, right? And control them. All these properties are understood. When you say we don't understand, I don't know what we don't understand. What we don't see, we don't understand is obvious, because something in universe, we might have a hypothetical view is that all this is possible, but we need evidences. Whatever we have, whatever lights we are getting from universe, from across the universe, everything, photon is a simple energy packet which has h mu, or what we call the energy of photons. It depends on the frequency, and that is the energy package which you are getting. They don't interact with anything very easily, and they remain inherent. So because they don't interact, we can't build molecules using photons. They don't stay. They all travel at the speed of light. To confine photon is very, very difficult. It's very easy to say photon, but they are given a chance, they are traveling at the speed of light. So from that point of view, what we don't know, what properties we don't know, we understand them well. So beyond that, I don't know what we can answer, but it's just left to further research to see.
Okay.
Thank you, sir.
So thank you, sir. I think we are coming at the end of this program. So before going to the end, let me just say a few words that we are really happy to have you, sir. It is very nice talk, and in future we are, if you are planning to do some workshop like things, we again contact you if possible. In spite of your very busy schedule, if possible for you, please join us.
Sure,
This
I'll be
this
happy.
kind of academic activities. I would like to express my sincere thanks to you. I'd like to express my sincere thanks to all the participants and all the faculty members of our department, our Dean Sir, Professor Aparajita Bhattacharya Madam, Professor Bimal Kumar Sarkar Sir, and I also like to thanks to our students, because for them only we are actually going to organize this kind of programs. And finally, I would like to thanks the support team of Adamas University. They give us a nice platform so that even if in this situation, we can continue our academic discussion sitting in a room. So considering all this, there is a happy end, and this is not an end, this is a beginning, and we will again contact you, sir. So thank you very much from my side, and I would like to request Professor Tamal Kumar Mukherjee to say a few words and conclude.
Okay, thank you again, Dr. Chandrasekhar, for taking your time and nicely explain all the questions, queries, and for your nice presentations. Hope to see you again somewhere, sometime. Okay, thank you very much.
Sure, thanks to all. It was wonderful talking to you and interacting with you all, and I'll be happy to collaborate more with time. Yeah.
Okay, sir. Okay, sir. Sir, one small question.
Yeah.
Can I ask, sir?
Yeah, please.
Sir, actually, in this present time, means is it possible that if some of our students can go and do some internship kind of work at your institute, is there any opportunity?
So we have visiting students program, and many students do apply and then come, depending on how many of them we do. We do have this opportunity of visiting student program. Okay. They can apply from our websites, and currently I'm not at IMSC. I'm at Indian Institute of Sciences, where we are doing some work here on things, but they can always write to us. And it's a science for everyone, right? We all have to progress, and students' interactions are very important. Yeah, if they can just write to us and express interest, and they can do. There are many students from different institutes who are even doing their master's thesis with us. But for a given time, in a given year, there is only few students we select. Sometimes they're just, we would have a number of students we will not take. It's nothing to do with them being good or not. It's just that we can't help them. If we take students, then we have to also help them, to give them time so that they learn something with it. But any students who are interested, they can always write to us, and we can work out some way of involving them with the project, working with them.
Okay, thank you, sir. Thank you, sir. So it will be a great opportunity for our department and our students also.
Yeah, sure.
Come on. Okay. So thank you very much. Thank you.
Okay, yeah. Thank you. Bye.
Okay.
Thank you.
Yeah.
Thank you. Tamal sir, so I think it is Okay.